Hello everyone, welcome back. This is our video solution for problem 2a from the first quiz. And here we're going to be computing antiderivatives. In principle, we say, well, this is just a function, but it's a sum of functions. And just like with the derivative, we know if we want to compute an antiderivative, we can do it sum end by sum end. So let's see, what do we need here? Again, I'll give a name to this function. We'll call it f of x. And so I'm trying to compute an antiderivative for f of x. Notice I'm saying an antiderivative, right? Not the antiderivative. One thing you probably learned in your Calculus 2 class, maybe even Calculus 1, is that there isn't just a single antiderivative for functions, right? There's going to be an infinite family of antiderivatives, except they all differ by a constant. So if you write down one, you sort of know them all, because all the others, you could just add a constant to it, and you'd get one of the others. We are just going to write down an antiderivative, meaning just one of them. So we don't need to write down a plus c or a plus anything at the end. We're just going to choose a specific one. So let's see. We're going to start here with a couple of power functions, and there is a wonderful little power rule for antiderivatives, which tells you an antiderivative of x to the n is 1 over n plus 1 x to the n plus 1, as long as you don't kick a puppy, right? Kicking a puppy is when you divide by 0. This is no good if n is equal to -1. So if n is equal to -1, that's no good, so we need to assume n is not -1. All right. Well, we'll talk about what happens when n equals -1 in a moment. But in this first instance, x cubed, well, the exponent is 3, and 3 definitely does not equal -1. So our antiderivative for the first sum end is going to be 1 over 4, right? So 1 more than the exponent times x to the 4th. All right, what comes next? Well, now our exponent is a -1, so we need to handle that situation. So if n does equal -1, we have x to the -1, or 1 over x. An antiderivative is the natural log of the absolute value of x. All right, don't forget these absolute values. They are absolutely essential unless you know your x is positive. So this would become minus the natural log of the absolute value of x. All right, how about this next one? Well, there's a little bit of a trick here. This actually looks a lot like 1 over x. There's this little shift, right? But it's essentially 1 over x. And remember, 1 over x equals x to the -1. So this feels like it also should be a natural log. And in fact, it is. So this will be the natural log of the absolute value of x plus 1. Now, maybe that's not obvious, so you might try taking a derivative, right, to check. You can always check your antiderivatives by taking derivatives. So if I have the derivative of the natural log of the absolute value of x plus 1, this is going to be 1 over x plus 1 times the derivative of x plus 1. But the derivative of x plus 1 is just 1. So, okay, we really do get 1 over x plus 1, which is what we want. Okay, moving along. Here we have 3 times something, and just like with differentiation, you have a homogeneity property for anti-differentiation, where you can more or less ignore this constant until the end, right? So I'll just write plus 3, and we can just find an antiderivative for e to the 2x minus 1. Now, just like with the derivative of e to the x being e to the x, of course, an antiderivative of e to the x is e to the x. So this isn't quite e to the x. It's got this 2x minus 1 business. But what I recommend students do, I mean, you could use substitution here, but I think it's a waste of time mostly, is you just guess what the answer is, right? You just guess, it's going to be the same thing. And then in your mind, you say, okay, well, let me take the derivative to check. And when I take the derivative of e to the 2x minus 1 will be e to the 2x minus 1, but then times the derivative of 2x minus 1. You'll have to use the chain rule here. And that's going to give you an extra times 2. Well, I don't want that extra times 2, so I divide by a 2 to compensate. Okay. Again, you could use substitution. You'll get the same answer, but it's a lot faster just whenever you compose with a linear function, just to divide by the, well, if you like, the slope, right, or the coefficient of the x term. Okay, moving along to the cosine. Well, we saw last time that the derivative of sine is cosine, so an antiderivative of cosine is sine. So let's see, we're going to get minus sine, and we do play the same game here. We'll just pretend we knew what was going on and that it's going to be sine of 7x, and then we check it by taking the derivative, and that's going to give us an extra 7 when we apply the chain rule. So we divide by 7 to compensate. Nice. Okay, what comes next? Well, let's see. We have the cosecant squared. So we need to know a function whose derivative is cosecant squared. So last time we saw that the derivative of tangent was secant squared. And so in fact, the derivative of cotangent is negative cosecant squared, which tells us that an antiderivative for cosecant squared is going to be negative the cotangent. Okay, so we come back up here. We are going to want, well, we have a plus, but we just saw we're going to get negative a cotangent. So let's do minus the cotangent. And again, we're composing with a linear function. So we just guess that we keep it there. And then if we took the derivative, we would use the chain rule and get an extra times 3. And so we compensate by dividing by 3. Okay, and then what's the last one? Well, 1 over x squared plus 1. Let me tell you what the answer is first, and then let's talk about what most people at some point try to do. So we actually saw in the solution to problem 1a that the derivative of the arctangent is 1 over x squared plus 1. So an antiderivative of 1 over x squared plus 1 must be the arctangent. Fantastic. There we go. And we just finished, right? Okay, but what's the common mistake? And we'll do this in red. Common mistake. People will say, oh, hey, you know what? We saw this problem over here. What's an antiderivative for 1 over x plus 1? Hey, it was natural log absolute value of x plus 1. And so this must be natural log absolute value of x squared plus 1. Okay, it's not unreasonable to think that might be true, but what can we always do to check? We take the derivative. So let's take a little derivative here. If I take the derivative of the natural log of the absolute value of x squared plus 1, we'll get 1 over x squared plus 1 times the derivative of x squared plus 1. Got to use that chain rule. And that gives me a 2x. Right? So this equals 2x over x squared plus 1, which is decidedly not the same as 1 over x squared plus 1. I didn't get back the function that I started with. So, nope, does not work. Okay? The only time you're allowed to use this trick, right, of saying, oh, it's 1 over something and the antiderivative's got to be natural log, is when that something is a linear function. Okay, so let's record that. So what is true, antiderivative of 1 over ax plus b. This will equal the natural log absolute value of ax plus b. And then you take the derivative and you say, oh, by the chain rule, I get an extra a. So I have to compensate by dividing by a. So that you can always say. As soon as you replace ax plus b with something which is not a linear function, you're almost certainly going to write down something which is false. Okay, so you can only ever write down the natural log when you've got 1 over a linear function.